Let me now look at this part of the motion in more detail. I also want to estimate, make a reasonable estimate of how many times the car would oscillate. Typical car would oscillate every second, and get a better understanding of this problem. So I'm just going to redraw this part more clearly. So let's start with this. There is this axle. This is the axle of the wheel. It is not my little yellow ball. And the body of the car, this is the body of the car. Okay, let me draw that here. This is where the body of the car, the part which is supported by the spring, for example, and this is the suspension spring. Let's say it's here. That's the spring, and there's a wheel around here. There's a wheel around here, and when the wheel goes over a step, and the wheel goes over a step. Let me try and draw that here. Say there's a step here, and the wheel has to go over this small step. Now, the axle, the wheel moves up, and with it, the axle, the wheel. So the axle comes up to a higher position. Alright, but over this very short time, the car, because the car has a big mass, it needs a little more time to respond. So at the first fraction of a second, alright, the car would still be hardly moved. It will still be at about the same level, and as a result, the spring gets compressed. Spring gets compressed. Alright, and that's the start of our oscillation. Because the spring is compressed, it will start pushing the car up. Now we can imagine that there is that there would be a new rest position. That's like the old rest position where the car stays at the same level if there is no bump. Now when it's here, just after the step, the spring is compressed. Okay, so let me just draw in. Right, let me just draw in this part a bit in case it looks odd that this thing is suspended above the ground. So there's supposed to be a wheel here. Okay, there is supposed to be a wheel here around the axle. Okay, but I'm just going to focus on the axle. So that's the wheel and that's the body of the car. I'm just going to focus on this part, so I'm not going to look at the wheel anymore. But the axle would just go along this level, all right, as the wheel rolls forward. And the car's body is what I'm interested in now. I'm interested in how the car body starts moving and starts oscillating. So let's try and understand this better. Okay, so because the spring is compressed, the car's body has a new rest position. It will be somewhere higher up. Now let's say it's somewhere there. So suppose that this is the new rest position of the car. Okay, So the compressed spring would stretch and push the car up towards the rest position. Okay, but of course it will okay, not of course, but it may overshoot, and then if the damping has not been adjusted properly, if it overshoots, the car would go up and down a few times, maybe before the resistance causes it to stop oscillating. Okay, or if the resistance is well adjusted, the damping is adjusted properly, the car would just move, the level of the car would just move towards its rest position. Okay. So this is what it will look like if the car oscillates. The car oscillates, then as the car moves forward, you would expect to see this point to follow what looks like a sine or cosine curve. Right, it will just go up and down, and the amplitude will decrease after some time, and then it will stop oscillating. And if it is well adjusted, it will quickly come to a rest here. It may quickly come to rest, and the car would smoothly move to its rest position, and everyone in the car would feel quite comfortable without that oscillation and the feeling of the sudden bump. Alright, so that's the situation. Now what I like to do now is to estimate the frequency of this oscillation if it happens. Okay, and estimate the time it takes for the car to recover to its rest position if it is well adjusted. Now we can actually make some reasonable estimates of this. So let me start. Let's see what we need to find the frequency. To find this frequency, let's think about the equation and the solution for a simple harmonic motion. Now the equation for simple harmonic motion is acceleration is equal to minus of omega squared x. Alright, and the solution we have already seen is x is equal to the amplitude times sine omega t. Alright, sine is just one possible solution. It can be cosine, or I can have some other numbers added to the t in these arguments. Okay. Now, but which part of this is related to the frequency? It is the omega. If you remember from an earlier session, the period, meaning the time for one oscillation. Okay. The time would be time for one cycle of this. Let me draw that, which is usually written as capital T. So this period is equal to 2 pi times omega. Now, if I want to find the frequency, I can, let's see, that the frequency in terms of the period, well, the frequency is actually the number of cycles per second, right? So number of cycles divided by the time. Now cycle here means how many times a motion repeats itself. So in this case, one up-down motion is a cycle, or we can say one oscillation. So in terms of the period, if I think about the time as one period, okay, let me make substitutions now. If I think about the time as one period, then the number of cycles in one period is just 1. So that gives a simple formula relating period to frequency. It's just 1 over big T. Now then I can also think about this. Come back to this equation now and think about what it means. It also involves a T. Let me rewrite this. Let me rewrite this to make omega the subject. So I'm just going to exchange the omega and the T. Get 2 pi over T. If you compare those two, see I have 2 pi over T here and I have 1 over T here. And 2 pi, if you remember, corresponds to, it means 2 pi radians. That's an angular measure. And it corresponds to 360 degrees. That means going one round around a circle. In an earlier session, I've talked about how this motion can be related to motion in a circle. Okay, so because of this connection, omega, you can think of omega here as the angular displacement per second. In other words, is like angular velocity, okay, in a circular motion. But if you're just talking about simple harmonic motion, that we're not really looking at circular motion. So there is another name that has been given to omega. Instead of calling it angular velocity, it is for when we apply this formula, this number to oscillations, we call it angular frequency. Angular frequency. So this is as opposed to F, which is the frequency. Okay, and the frequency, the units for frequency is hertz, as in cycles per second. But for angular frequency, it's not hertz because you have the 2 pi there, so it's radian. It's actually radians per second. Okay, so these are what we need, and in order to find the frequency, how many times it oscillates, we actually need to know we actually need to know the period or the angular frequency, if we can somehow estimate that. Now, and what we need to do then is to think about some reasonable estimates of about the spring and say the mass of the car, and relate it to omega. Now, if you recall the relation, if you recall that there's a relation between the mass and spring constant and the angular frequency from the earlier session, you can write this down. Omega, let's see, omega squared is equal to the spring constant divided by the mass. So if we can somehow estimate the spring constant and the mass of the car, then we can actually use this relation to find, and this one to find the frequency.